Okay. So welcome back for our chemistry class. Come back to this chemistry class where we are looking at physical chemistry. And in physical chemistry, in particular, we are looking at a topic called chemical equilibrium, which is part of equilibrium 1. Yeah. So, like I said earlier, in this part, the element of construct or the construct examines 3 areas of 4, equilibrium 1 and 2, and then moles and equations. So I want us to pick it up from where we stopped last time, and then we proceed with the things we were doing. So by the time we left, we were looking at a number of calculations in this topic. We looked at calculations to do with chemical equilibrium, and we said that they contribute or constitute around 70% of this topic. So 70% of equilibrium or physical or chemical equilibrium is actually calculations. And I want us to maybe streamline it a little better by looking at these calculations in sort of like cases. So we looked at case 1 of this calculation, where you have been given equilibrium moles, where you have equilibrium moles. And your intention in this case is to calculate the Kc and the Kp. We need to understand the importance of calculating that, but that one we shall look at it a little bit later. But for now, we need to first know how to calculate. Are we able to compute Kc and Kp expressions and also to calculate their values? Okay, so in case 1, we looked at how to calculate equilibrium moles, and I want us to pick some simple example as a reminder of this case, and we see how that happens. So let's say we have a number that says, this is our number 1, it says initially we have 2 moles of hydrogen being placed in a vessel with 1.5 moles of iodine, and at equilibrium, they found out that 0.8 moles of hydrogen, 0.8 moles of hydrogen had reacted. 0.8 moles of hydrogen had reacted. So our case 1, I want to streamline it a little better. Our case 1 is going to be equilibrium moles, or let's say they've given us moles that reacted. How would we handle a case where we've been given the moles that reacted? How would we go about that? So we have such a question that says, initially we had 2 moles of hydrogen and 1.5 moles of iodine, and at equilibrium they found out that 0.8 moles had reacted. So what is our intention? Our intention is to determine the Kc for this particular equilibrium. Remember, we call them systems. The Kc for this system, which is the equilibrium constant, the concentration equilibrium constant, and we shall also go ahead and get the pressure equilibrium constant. Okay, so if you get hydrogen and you place it in a vessel, just a minute. If you get hydrogen and you place it in a vessel with iodine, both of them being gases, you're going to get, we said it should be reversible reaction, you're going to finally get what we call hydrogen iodide gas. So when you mix those two, you get hydrogen iodide gas. And they are telling us this is what we are going to always be thinking about. We are always going to be thinking about what I normally call the ice table. So in these calculations, we are preparing ice. And sometimes we can either get that ice and we coat it with something, or we get the ice and we pot it. So you can either coat the ice or pot the ice. When I say P, I mean pressure. When I say C, I mean concentration. And then when I say the first I stands for initially or initial moles. That I is standing for initial. What do we have initially? Then when we say C, we are referring to change, the change in moles. And then when we say E, we are standing for the moles at equilibrium. What are the moles at equilibrium? So when you are drawing your ice table, a number of things you need to consider is first, you need to know your initial moles. What moles changed? They could be formed or they could have gone away during the reaction. What are the moles at equilibrium? And finally, what is the concentration or what is the pressure? Now, whether you get concentration or pressure depends entirely on the number that they're interested in. If the question is asking for Kc expression, then you need to get concentration because Kc is concentration equilibrium constant. But if the question is asking for Kp, then that means you need to get pressure. So when you get pressure and when you get concentration depends entirely on the particular scenario that you are dealing with. So here they are telling us that initially we had 2 of hydrogen and 1.5 of iodine. So we had 2 of hydrogen and 1.5 of iodine. These are the 2 guys we are going to place in our vessel. So they were placed in a vessel. The vessel was closed, and we understood the intention behind closing this vessel is to ensure that our gaseous reactants don't escape. Because they are gaseous in nature, they could escape if you open the vessel. So we close the vessel, and then they start reacting with each other. Now, initially, at the start of maybe this experiment, we don't have hydrogen iodide at all, because what was placed in the vessel is hydrogen and iodine. That's the only thing we placed there. Hydrogen iodide, its number of moles was 0. Okay. And what other information has been given? They are telling us when they came to check at equilibrium, 0.8 moles had reacted. Now, there is something we need to note here. Very importantly, a few words that we are going to use. Words like whenever you see reacted, dissociated, decomposed, reacted, dissociated, decomposed. All these three words in chemistry, they mean a similar thing. And they mean the disappearance of something. If something reacted or dissociated or decomposed, it is going to disappear. So all those three words mean something is disappearing or something is changing from what it was to become something else. Okay, let's bring that science back to this other side. So whenever I use those three words, reacted, dissociated, decomposed, I'm almost meaning a similar thing. I'm trying to tell you that 0.8 moles disappeared. Okay. Now, if you were sent to a shop with 1,000 Ugandan shillings, and then you buy a sweet of 200 Ugandan shillings. How much disappeared? 200. The amount of money that you used is the one that disappeared. And when we check, we shall find you with 800 Ugandan shillings. Why do we find you with 800 Ugandan shillings? It's because part of the money we gave you, which is 200 Ugandan shillings, you have used it to buy the sweet. Now you have only remained with 800 shillings. That is a similar thing. If members, you had 2 moles, and we are saying that 0.8 is disappearing, 0.8 of it, you initially had 2, and they're saying 0.8 disappeared. When you see this word, they're telling you disappeared. 0.8 moles of hydrogen had reacted. This is moles of, I guess I need to indicate it, moles of hydrogen. So if they disappeared, then that means that becomes the value of the amount of moles that changed, the amount of moles that changed. Now, if you had 2 and you took away 0.8, chemically speaking, the 0.8 reacted. But in terms of English, we are saying it means disappearing, it means a removal of something. So 2, you had it 2, you took away 0.8, automatically you remain with 1.2. How did I arrive to 1.2? Now, for me to be able to arrive to 1.2, I've used a similar science like the one here. If you had 1,000 and you used 200, automatically it means you have remained with 800, which is simply the 1,000 minus the 200. So it's a similar thing here, that I had 2 minus the 0.8 finally give me 1.2. Okay, a second thing to note. Number 1, we have said whenever you see these 3 words, reacted, dissociated, decomposed, what should be coming to your mind is one thing, and that is these are the number of moles that disappeared, that went away during the reaction. Okay, number 2 that we need to note is when we talk about equilibrium. You see, I've explained equilibrium a number of times, but mathematically speaking, I want to make it clearer. When we say equilibrium, we are talking about the final state of the system. What do you find when you come to check your vessel? That is what you finally have at equilibrium. So what is the final state of the closed vessel that we had? We initially had hydrogen, we mixed it with iodine, they start reacting. We leave them to react until no more reaction can occur. When such a thing happens, then we say equilibrium has been achieved. And members, we said in chemical equilibrium, because we are dealing with reversible reactions, then at equilibrium, we are going to find both the reactants and the products. So it behooves us to know what has remained. What is at equilibrium is what has remained. In this analogy that I've just given here, now, what would be the equilibrium equivalent is the 800 Ugandan shillings, the amount of money you've remained with. So whenever you see the word equilibrium, a few words or a few things should come to your mind. Firstly, you're thinking about the remainder. After the reaction, what exactly remained? Or you're thinking about moles that are there finally. What do we have finally after everything has happened? What do we have at the end of the reaction? That is what we call equilibrium moles. These 2 statements are looking very simple and direct, but that is where chemical equilibrium calculations rotate around, because later I'm going to be interchanging those words at ease and at will. So you should be with me when I say at equilibrium, the moles at equilibrium. The moles at equilibrium, then what should be coming to your mind? These are the final moles, or these are the moles that remain after the reaction had occurred. But when I say moles that reacted, or moles that dissociated, or moles that decomposed, then you should be thinking about the change in moles. How many moles disappeared, how many moles went away, or how many moles were used during the reaction. Now, when these chemicals or substances are reacting, they react in a particular way. And the way they react brings me now to a term which I've been speaking about, a term called stoichiometry. Now, this equation you see here is a stoichiometric equation. I could write the spelling here. Stoichiometric equation. And according to this stoichiometric equation, it tells us that always 1 mole of hydrogen, when it meets 1 mole of iodine and they react in a closed vessel, they are always going to give us 2 moles. However, one thing we should note is that the moles that are in the stoichiometric equation usually are not the experimental moles. Now, when I say experimental moles, I mean they are not the moles that were involved during the reaction. So we need to know how many moles were there in the reaction. Already they've told us that for hydrogen, they were 0.8. The moment you know the number of moles for one of them, then the standard is you can always get to know the number of moles for all the rest of the chemical substances in the reaction. How do we do that? Using stoichiometry. So they are telling us that 1 mole, okay, the science is, let me rub this off. Let's rub this off and I streamline it better. They're telling us that if you have hydrogen reacting with iodine, when 1 mole reacts, it will react with 1 mole. But in our equation, was it 1 mole that reacted? No, it was 0.8. So if 1 mole reacts with 1 mole, how about 0.8? They're going to react with 1/1 times 0.8. And that, members, will finally give us 0.8 moles. These are what? For hydrogen iodide. So we come here and fill our hydrogen iodide comfortably with a 0.8. They're telling us that this iodine was initially 1.5 moles. Now, members, if it was initially 1.5 moles and 0.8 were used during the reaction, because we said these are the moles that are being used during the reaction. So if you had 1.5 and 0.8 were used during the reaction, that means you're going to remain with 0.7. That's what you remain with, 0.7 moles. Okay, how did I arrive to 0.7? I initially had 1.5. I used 0.8. And if you had 1.5 and you used 0.8, what does that tell you? That finally you have remained with 0.7. Because if you have 1,500 and you buy a chapati of 800 Ugandan shillings, it's a pity that they are very few nowadays. You have 1,500, you buy maybe samosas for 800 shillings, you remain with 700 shillings. That is the science. That 1.5 minus what was used, you get what finally remained. Okay. That is for hydrogen and iodine. How about for hydrogen iodide? So for hydrogen iodide, we still use the one we know. They are telling us that if hydrogen forms hydrogen iodide, in the stoichiometric equation, we always, if you want to know, this should be a standard, that whenever you want to know the moles that reacted members, please pick the stoichiometric equation and use the mole ratio that is there. So the mole ratio tells us that whenever you have 1 mole of hydrogen, you're going to form 2 moles of hydrogen iodide. That is what the mole ratio tells us. But we ask ourselves a question. In this particular reaction, was it 1 mole of hydrogen reacting? No. It was actually 0.8. So if 1 mole forms 2, how many will be formed by 0.8? So 1 forms 2. How about 0.8? It will form 2 over 1 times 0.8, which finally gives us a 1.6 moles. Now, if we come to fill that in here, it tells us that initially we had 0. Now we have formed 1.6. So finally, we shall find ourselves with 1.6 moles. So what does that mean? If I try to minimize this, oh, that's a little error. I try to just a moment. Okay, I guess there it's back. I want to minimize it like that. Okay, so I've done a lot of writing here, but I want us to pick it. So what we are saying is this, that you had 2 moles here. You had your 2 moles here, these 2 moles, and now they are telling us that 0.8 reacted, you remain with 1.2. You had your 1.5 here, 0.8 reacted, you now have your 0.7. You had your 0, 1.6 was formed. Oh, that's a little error there. 1.6 was formed, and if 1.6 was formed, what does that mean? It means you're going to remain with 1.6. So if I draw for you a clean ice table, you have something like this. This is 2. This is 1.5. This is 0. This became 0.8. This was also 0.8. This was 1.6. And finally, we found out that this was 0.7. This was 1.6. And this was 1.2. And what are these? These are the initial moles. Then these are the moles that reacted or formed, and these are the final moles. That's the clean table. Where did I get the 2? It was given to me. Where did I get the 1.5? It was also given to me. Where did I get the 0.8? It was also given to me. How did I get this 0.8? I used mole ratio. So where do we use mole ratio? We use mole ratio on stage 2. Very important to note. Mole ratio is used on stage 2. That's where we use it. The moment you have the number of moles for only one of them, then we can always use mole ratio to get the number of moles for the other. And if you know the moles that reacted or formed, it's like telling you, you know what you have, how much money you have initially, and you also know how much money was used. Finally, you can be able to get the amount of money that finally remained at the end of it all. Okay, I want to take this a step further, and we look at another example, which I'll call case 2. So case 1 was when you have been given the moles that reacted, or the moles that dissociated, or the moles that decomposed. I repeat, the very first statement you need to understand is how we use those chemistry words. When I say moles that reacted, let me go back a little bit. When I say moles that reacted, or moles that were formed, okay, moles that decomposed, moles that dissociated, I'm telling you what is here on stage 2. So when I say 2 moles of hydrogen decomposed, 2 moles of hydrogen iodide decomposed, it tells you that I've given you the moles that went away or that disappeared. But when something disappears, something remains. Now, what remains is what we find at equilibrium. So those two things shouldn't be confused. What usually confuses learners is when I say at equilibrium, 2 moles reacted. Now, that statement is a little bit contradictory to some learners, but actually it is not contradictory. The reason is, it's like telling you, when I came to check finally, I found out that 2 not had remained, but 2 had gone away. So still, even if I say at equilibrium, 2 moles had reacted, still I've not given you final, even when I've used the word equilibrium, still I've given you moles that reacted, because I've said moles that reacted. When I want to give equilibrium moles, I'll not put any condition. I'll say these are the moles at equilibrium. It was found out that 1.5 moles of hydrogen were found at equilibrium. But when I say at equilibrium 1.5 had reacted, that means those are the non-final moles. Those are the moles that reacted during the reaction. Okay, let's go to case 2. Let's look at case 2. So case 2 is when I've given you the moles at equilibrium. Case 1 was when I've given you the moles that reacted. Case 2 is when I've given you the moles at equilibrium. Maybe I want the case C. Okay, let's say I've given you, say, and I say at equilibrium, a 2 decimeter cubed vessel, a 2 decimeter cubed vessel. This 2 decimeter cubed vessel contains what? Contains 0.4 moles of hydrogen, 0.30 moles of iodine, and 1.2 moles of hydrogen iodide. What have they given us, members? They've not told us that they reacted. They've not told us they decomposed. They've not told us they dissociated. What they have told us that these are the moles at equilibrium. So it's like telling you, let me see, what did we have? Hydrogen, iodine, okay? It's like having your hydrogen combining with iodine, you finally get hydrogen iodide. So initial moles not given, moles that reacted not given, equilibrium moles given. And equilibrium moles, they are saying that we have 0.4 of hydrogen. How many of iodine? 0.3 of iodine, and then 1.2 of hydrogen iodide. And the question is saying that you calculate actually the case C. Now, if I want case C, it means I want concentration. So that means I want concentration. How do we get concentration? Number of moles over volume. That is something we have seen already. So it will be 0.4 over 2, 0.3 over 2, 1.2 over 2. Why am I dividing by 2? Because my volume is 2 decimeters cubed. Take note, as we said earlier, that if that volume was in centimeters cubed, then when we are calculating our concentration, we don't only divide, but we also multiply by 1,000. But here we're just multiplying by 1, multiply by 1, multiply by 1. But if it was in centimeters cubed, that 1 becomes 1,000. So it would be 0.4. If it was maybe in a 2 centimeters cubed vessel, it would have been 0.4 over 2 times 1,000. But since I'm dealing with decimeters cubed, all liters, I don't need to multiply by 1,000. It is simply 0.4 by 2. That gives 0.2. 0.3 by 2. That gives a 0.15. This is concentration, molar also concentration. 1.2 by 2, that gives a 0.6 molar. Now, members, we have our concentration. And since they want Kc, since the question is looking for Kc, the concentration equilibrium constant. When I ask for Kp, then I want pressure, not concentration. But for this case, I'm looking for C. I want concentration. Okay. So let's write our Kc expression. So our Kc expression will be Kc equals to concentration of hydrogen iodide squared over concentration of iodine times concentration of hydrogen times concentration of iodine. So it will be equal to 0.6 squared divided by 0.2 times 0.15. So up there we shall have 0.36 being divided by, let me get my calculator very fast here. So 0.6 squared is 0.36, while 0.2 times 0.15 gives a 0.03. And finally, what does that give? So 0.36 divided by 0.03 finally gives 12. So our Kc equals to 12. I say that every calculation of physical chemistry must have 3 parts. Part number 1 is the formula you are using. Part number 2 is correct substitution into the formula. So the formula you are using, correct substitution into the formula. The rest of this is mathematics. And then we want to see the final answer. Those are the 3 parts. The formula, correct substitution into the formula, and then the final answer. And our final answer, we said, has 2 parts. It has a value. It also has its units. Now, we say the units are derived. So if we want to know the units for this one, It's like telling you it was molar squared divided by molar times molar. So 2m and 2m. The m's are squared up. They are not 2, but they are squared. M times m. Even down, we have m times m. So this goes with this. And finally, this case C will not have any units. So the answer is this. And we say no units. No units. So if I try to minimize this again, such that the number looks complete, that is how the number looks like. At equilibrium, a 2 decimeter tube vessel had 0.4 moles of hydrogen, 0.3 moles of iodine, and 1.2 moles of hydrogen iodide. Calculate the Kc. So to get Kc, I needed concentration. And concentration is equilibrium moles divided by volume. That is how we get concentration. Equilibrium moles divided by volume. So I got my equilibrium moles, divided them by the volume I had, I got the concentration. Now, after getting the concentration, I calculate the Kc by first stating the formula, secondly, substituting rightly into my formula, and then thirdly, finally getting the final answer. And the answer has the value and its units. Those are principles that you should be moving on with the moment you start doing a calculation number of chemistry. Okay, that's very good. I want us to take this a step further. Now, before we go far, or before we look at another example, you notice that I didn't go back to initial moles. I didn't ask myself again, what did I have initially? I didn't need initial moles. I didn't need equilibrium, change in moles or moles that reacted, because I already have what I have finally. So the moment you have the moles at equilibrium, you already arrived at the answer you want. Just proceed and go on with the question as per asked by that particular examiner. So that is what we do in case 2, especially if you've been given moles at equilibrium. So when you have moles at equilibrium, go direct, write them there, proceed to get concentration, and then from concentration, finally, calculate your Kc expression as we desire it. Okay. Today, I came to destroy chemical equilibrium. That is case 2. So what was case 1? Case 1 was a scenario where you have been given the moles that reacted or moles that decomposed or moles that dissociated. Whenever you see those words, then remember we have 3 things we are feeding. Either you're feeding in I, or you're feeding in C, or you're feeding in E. So when I say moles that reacted, C. Moles that decomposed, C. Moles that dissociated, C. Initial moles, I. Equilibrium moles, E. Final moles, E. So the moment you hear the word, something should be clicking. Where does this fall? Where does this fall? Where does this fall? So that is the kind of technicality that is here in this calculation. The moment you're able to notice that, calculations of chemical equilibrium are going to be as easy peasy as taking a bottle of water. So I want us to proceed to case 3. What we're actually doing is just identifying where do we place the moles that have been given to us? Where exactly do we place them? And then if that is clear, I'll proceed on to the gist of today's lesson. I'm breaking it down step by step in a more organized fashion. Okay, I want us to do case 3. Case 3. Okay, here we are with case 3. We try to make this a little bigger. Okay, case 3. Now, case 3 is when you know the initial moles plus equilibrium moles for only one. You know the initial moles plus the equilibrium moles for only and only one of them. That is our case 3. You know the initial moles and the equilibrium moles for only one of them. How do you go about such a scenario? So let's pick a case example. This time I'll use the mole ratio that usually disturbs learners. I'll use nitrogen. Let's say our question says, initially, we said we have initial. So initially what do you have? You have 2 moles of nitrogen. What else do you have? 6 moles of hydrogen. And we are placing them in a 4 decimeter tubed vessel. You have 2 moles of nitrogen and 6 moles of hydrogen, and you are getting them and placing them in a 4 decimeter tubed vessel. Okay. And we're finding out that at equilibrium 1.2 moles of nitrogen remains. And then I ask you to calculate the Kc. Okay, a little bit back here. We have the initial moles. Case 3 is a case where you have the initial moles plus the number of moles for only one of them at equilibrium. So how do you deal with that? And they're telling us that initially, the initial moles for hydrogen are 6. For nitrogen, they are 2. So they got 2 moles of nitrogen, mix them with 6 moles of hydrogen in a vessel which has a volume of 4 decimeters cubed. And then it was found out that at equilibrium, we only had 1.2 moles of nitrogen. So how do we deal with case 3? Let's handle case 3 and we see how we finally get the case C. Okay, our ice table again. Members, this is what we are doing. We are either feeding in I or feeding in C or feeding in E. That is our ice. So in this case, we have nitrogen, we have hydrogen, and we have ammonia. Now you may ask, where did ammonia come from? The science is that when you get nitrogen and you mix it with hydrogen in a vessel, they don't just there and look at you. They start reacting. But when they react, this is called the Haber process. They form what we call ammonia gas. And if you have to balance with the 2 there and the 3 there, finally it becomes balanced. Remember what is the importance of ammonia, of that stoichiometric equation? That chemical equation helps us to get the mole ratio, which we finally use to get C. I repeat, why am I interested in the stoichiometric equation? It's because when I have that equation, I can use it to get the C for the ones that I don't know. That is very important information. When you pick that, wow. Chemical equilibrium, very easy. Okay, let's fill in our table and we see what we are missing and what we have. We have 2 moles of nitrogen initially. Nitrogen initially 2. Hydrogen initially 6. I for hydrogen is 6. But did we have ammonia initially? No, it is 0. So our initial is totally filled. Okay. How about our C? Let me see if C has been given. The rest of the information we have is equilibrium moles, which is 1.2. So they're telling us that 1.2 moles of nitrogen were found at equilibrium. That is the only information you are given. So members, we don't know this one. 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 Okay, it's a puzzle. Let us solve the puzzle. So members, if you go to the market with 2,000 Ugandan shillings, which is our 2, and you only come back with 1,200, what does that mean? You have used some amount of money. Some 800 shillings has gone. So how do we get the change in moles after we have the equilibrium moles? So if you had the 2 and you remain with 1.2, it means you have used the 2 minus 1.2, which will be equal to 0.8. Okay, so it's no longer a puzzle because one part of the puzzle has become solved. So what was an empty box now is filled with a value. Which value is that? The value is 0.8. Okay, so we have 0.8 moles of nitrogen. The moment you have only one C, say hallelujah. Thank you, Jesus. Thank you, Lord. Wow. The moment you have one of them, it means you can get the others. How do you get the others? By using the equation. That is why this arrow, members, becomes very, very important. Which arrow? The arrow that takes me to the equation. What does that equation tell me? That equation tells me that if I have nitrogen, you start with what you have. What do I have? I have nitrogen. And this nitrogen is reacting with hydrogen. But the equation is telling us whenever 1 mole reacts, it will react with 3 moles. But did 1 mole react in this equation? No. How many moles reacted? 0.8. So if 1 mole reacts with 3, how about 0.8 moles? They are going to react with how many? They are going to react with 3 times 0.8, which gives 2.4 moles of hydrogen. So we come beautifully here and say, wow, the puzzle is solved. So we get our 2.4. If we want to solve this also, we do a similar thing. This time we're starting with what we know, going to where we don't know. What do we know? We know nitrogen. What don't we know? We don't know ammonia. And the equation tells us, members, that whenever 1 mole of nitrogen reacts, it forms 2 moles of ammonia. But this time it was not 1 mole, it was 0.8. It's going to form 2 times 0.8, which is 1.6 moles. So we come beautifully here and write our 1.6. Wow. So I is filled, the row for I is filled, the row for C is also filled, and the row for E is also filled. Wow. What does that tell us? These are the only boxes that are not filled. Okay, how do we fill them? Usual way. If you initially had 6, you use 2.4, you're going to remain with the 6 minus what you used. 6 minus 2.4 will finally give you a 3.6. So you remain with 3.6. Now, it is important to note that for reactants, we are actually subtracting because they are reacting, they are being used, meaning they are disappearing. So we are subtracting. In mathematics, how do we represent a disappearance of something? It means you represent it using a minus. So whenever you see in mathematics a 6 minus 2, it means the 6 you remove 2. So here in chemistry, the removal is the reaction. They reacted. However, when we are forming, if you don't have anything and someone says, oh, my dear friend, get some 2,000 Ugandan shillings. You had 0 Ugandan shillings and he added you 2,000 Ugandan shillings. Finally, that's when you come up with 2,000 Ugandan shillings. Those are the products. For the reactants, we are subtracting. For the products, we are adding. So if you started with 0 and you formed 1.6, you remain with 1.6. So members, we finally have our table full. That is a table full of ice. A beautiful table full of ice. Now, we ask ourselves a question. This ice, do we coat it or we pot it? If we coat it, it means we want concentration. If we pot it, it means we want pressure. So in this case, they are asking for K. C. Oh, beautiful. Kc means they're asking for C, which is concentration. So it will be moles over the volume, which is 4. This is concentration. Moles over the volume, which is also 4. Moles over the volume, which is also 4. So what does that give? It gives you a 0.3, a 0.9, and a 0.4. That is the concentration. Okay, but have we arrived? Not yet. What we only have is the concentration. Now we proceed to calculate the Kc using the concentration values that we have obtained. So what will be our Kc value? Our Kc will be equal to concentration of ammonia squared divided by concentration of nitrogen times concentration of hydrogen cubed. Remember, we are calculating. The first thing is the formula. Substitution into the formula, which will be equal to 0.4. The brackets, the square brackets end there, because now this is mathematics. We don't need the square brackets. 0.4 squared. The chemistry ends here. It's going to come back later in the answer. This is now mathematics. Divided by, what was the one for nitrogen? It was 0.3. 0.3 times the one of, you see, the one of hydrogen is 0.9 times 0.9 cubed. So what does that give? It gives a 0.16 divided by what we have down. So down we have a 0.3 times, just a minute, times 0.9 times 0.9 times 0.9, which gives a 0.2187. And when we get 0.16 divided by 0.2187, finally our answer becomes, I'm going to use for dp, 0.7316. So it means that our Kc is equal to 0.7316. We have arrived at the final answer. But the moment you ask yourself, have I arrived at the answer? Yes. Is it the required answer? Yes, but no. Why I can no is because the answer is not complete. When is the answer complete? The answer of chemistry, especially physical chemistry, is only and only correct if at all it also has the correct units, the correct derived units. So in this case, up we have molar squared, down we have molar times molar cubed. So it's like we have molar squared over molar power 4, which will be molar power -2. So that is the unit. And we know molar is moles at decimeters cubed. This is power -2, which finally tells you that this is moles power -2 decimeter power 6. So our units are moles power -2 decimeter power 6. So that is our final answer for the value of Kc. I'm gonna bring this and minimize it such that it becomes clearer. This was an illustration. I can rub it off so people can see things clearer. Okay. So if I try to bring this a little bit like this, a little bit more, yeah. There we are, members, with our calculation. So that is it in complete form. That is how it looks like. Question was saying initially we have 2 moles of nitrogen and 6 moles of hydrogen being closed in a 4 deciliter tubed vessel. At equilibrium, it was found out that 1.2 moles of nitrogen had remained. Calculate the Kc. So what I did firstly is to write the correct stoichiometric equation. After writing the correct stoichiometric equation, I went ahead and filled my ice table. After filling my ice table, I already have my ice. What does the ice give you? It gives you the number of moles at equilibrium. And the moment you have the number of moles at equilibrium, then the next thing, members, that should be asking yourself, oh, what is being asked? Is it Kc or Kp? If we go ahead and we look at ionic equilibrium, then something that will become very, very important is now Ka, Kb, Kh. Those will all start coming into play. But for now, we are looking at Kc and Kp expressions. So when I say Kc, I'm referring to the constant, equilibrium constant. K is for equilibrium constant, and then the C is for concentration. So for now, I'm looking for the concentration equilibrium constant. So you'll notice that when I do that, I first wrote the formula, which is right here. Just a moment. Which is right here. This is my formula. This one here, members, is my formula. After writing the formula, I proceeded to substitute into the formula right here. And you notice the brackets I'm using. These brackets, the normal ones. The square brackets, we use them only in chemistry here to mean concentration. When we go to mathematics and we're dealing with values, we bring back our normal brackets. Then I simplified it further. So this is just a simplification. If you're good at math, you don't need to simplify. But I always tell my learners, please be humble when you're solving numbers that have computation. Be humble, settle down, do it slowly, step by step. So finally, after you have this, if you divide this by this, you finally get this value. That is the value, but it is not the answer. The answer is value plus units. Very important. The answer in physical chemistry is the value plus units. So please don't just write a value, just a value, and you say, wow, I've rocked it. You only rock it if you have the value, but you also have the units for those values. So very, very important to note. So when I discovered that I only have the value, I proceeded to also get the units. How was I able to do that? Here I was. I noticed that up it was M. Where do I get M from? M is for concentration. So I had the concentration of ammonia being squared divided by the concentration of nitrogen, that one just power 1, times the concentration of ammonia, and that one was power 3. So if you have 2 up and 4 down, that's when I came up to this. And this, mathematically speaking, gives you this. However, this capital M is this. And finally, I arrived at my final answer, which is the final answer for the unit, which is moles per -2 decimeter power 6. Okay, so that is how we deal with our case 3. Case 1, you only have equilibrium moles. Case 2, you have moles that reacted plus initial moles. Case 3, you have moles at equilibrium plus initial moles. That is how we deal with them. Now, sometimes we reshuffle this. If you notice well, in this particular equation, let me go back a little bit to my question here. Here I gave you the moles. Here I gave you the moles of nitrogen. And you notice that nitrogen is a reactant. Now, I can still do a similar number for case 3, but this time when the moles at equilibrium that have been given are moles of a product. Let's see how we maybe deal with that. Still under case 3, but another example where the moles are at equilibrium, but they are for the product. Let's say we have been given, okay, let's keep it still at hydrogen and nitrogen to give us ammonia, or the opposite. Let's say this time we still have a 4 decimeter tube vessel. A 4 decimeter tube vessel. A 4 decimeter tube vessel initially contains 2.4 moles of ammonia. Initially contains 2.4 moles of ammonia. And it was found out that at equilibrium, at equilibrium 0.4 moles of nitrogen were formed. And they're telling us to calculate the Kc expression. That is what they're telling us to do, to calculate the Kc. They're telling us that a 4.0 decimeter tube vessel initially contains 2.4 moles of ammonia. At equilibrium, 0.4 moles of nitrogen were formed. Calculate the Kc expression. How do we handle such a case? Okay. Now, still, the very first thing, members, the very first thing is to write the correct balanced equation. The correct, I repeat, balanced equation. Now, what is the correct balanced equation in this case? When you want to know which you start with, ask yourself, what did they put in the vessel? So you notice that this time they didn't put nitrogen and hydrogen to give us ammonia. This time, actually, what they put in the vessel was the ammonia. So we are starting with the ammonia, the one they put in the vessel. So they got ammonia. Put it in a vessel. When you put it, it's going to dissociate to give us nitrogen plus hydrogen. That is how the equation looks like. This is a gas. This is also a gas. Next thing in line is to draw your ice table. So we draw our ice table. Your ice table tells you you have ammonia, you have nitrogen, you have hydrogen. You need to remember that this one is this time a reactant, and this time these ones are the products. And remember, on the side of the reactants, we subtract. On the side of the products, we add. So this is what we have. So you have your ice, your I, you have your C, and you have your E. You finally have complete ice. So you have your I, your C, and your E. Ice table. What does the information say? It is telling us that we had 2.4 moles of ammonia. 2.4, initially 2.4. And initially the products are always 0 and 0. And they're saying at equilibrium, 0.4 of nitrogen was formed. 0.4 of nitrogen was formed. Members, the moment you want to solve this ice table, which looks like a puzzle, start where you see only one unknown, the column where there's only one unknown. So if you notice, in this column, how many unknowns do we have? We have 1, 2. So it's the wrong column to start with. How about here? 1, 2. It's the wrong column to start with. How about here? Only 1. So we first solve where we have only 1. So meaning we are going to start with nitrogen. It's a product, and they're telling us that we started with 0. They're telling us that we started with 0. Then finally we found out that we have 0.4. It means that we have formed 0.4. Okay. So the moment you have one of them, the moment you have one of the C, remember you can get the rest by getting that C and reusing the stoichiometric amounts. Those are the principles we are going to always follow. So I know one of them. What do I know? I know nitrogen. This time I need hydrogen. And it tells us that 1 mole is formed with 3 moles. But this time there was 0.4, so they'll be formed with 3 times 0.4, which is 1.2. So there is a 1.2 here. Okay, now we only have 1 space. Oh, so we feed it. You had 0, you formed 1.2, so that means you have remained with 1.2. That is what you remain with. I come back this other side. I need ammonia. I start with what I know, going to what I don't know. I know nitrogen. I need ammonia. Okay, so they're telling us from the equation that 1 mole is formed from 2 moles. But this time it was not 1 mole, it was 0.4. So it will be 2 times 0.4, which will be 0.8. So this is 0.8. On the side of reactants, you subtract. So 2.4 minus 0.8 gives you your 1.6. So if you are keen enough, you will notice, members, that our ice table is done. And the moment your ice table is done, you say, hallelujah, you start rejoicing. Wow, my ice table is done. The moment it is done, proceed, ask yourself, what do they need me to do with this ice? Coat it or pot it. If they need concentration, it means they want you to coat the ice with some beautiful, maybe strawberry flavor, maybe whatever it may be, or vanilla flavor, whatever it may be. Are you coating it, or you are getting it and storing it in a pot by finding pressure pot? So our ice, they're telling us to capture the case C. If they want the case C, that means they want us to coat our ice beautifully well. So how do we coat the ice? If you want to coat the ice, you get the concentration. How do you get concentration? The number of moles that you have gotten, which is 1.6, divided by the volume. Our volume is 4. This is 0.4 by 4. This is 1.2 by 4. So this will give what? A 0.4 here, a 0.1 here, and a 0.3 there. Okay, that is our concentration. We don't stop by getting the concentration. We proceed and we calculate the Kc expression. So how would we calculate Kc? So Kc will be equal to concentration of the products raised to the appropriate powers, which this time is nitrogen times hydrogen raised to its appropriate power, divided by ammonia also raised to its appropriate power. This is the first thing when you're calculating. Write the correct formula. The moment your formula is there and you know it is correct, proceed again and substitute into the formula. So what is nitrogen? Nitrogen is 0.1. So 0.1, I drop the square brackets, I use the normal brackets. Time was 0.3 cubed divided by the 1 of ammonia is 0.4 divided by 0.4, and this is squared. Okay, so speaking in terms of calculation, what will that give you? 0.1 times 0.3 cubed. That will give you a 0.0027, and this is being divided by 0.4 squared, which finally becomes a 0.16. So 0.0027 divided by 0.16, 0.0027 divided by 0.16 finally gives you, I'll write to 4dp, 0.0169. That is our answer. But remember, that is not the answer, it is just a value. The answer should be the value together with the units. So Kc is equal to 0.0169 together with the units. What are the units? This time it was molar for nitrogen, and then the molar for ammonia cubed over the molar for ammonia squared. So this is nitrogen, this is hydrogen, this is ammonia. So it is m power 4 up over m power 2, which will be equal to m power 2. And we know that that capital M stands for moles per decimeters cubed. So if it is squared, then if you multiply and open the brackets, it will be moles squared decimeter power -6. Those are our units. So we come beautifully here and say Kc is 0.0169 moles squared decimeter power -6. So if I minimize this again, so that you can see in complete how my calculation looks like. Initially, that was the question. It was saying a 40 decimeter tube vessel initially contains 2.4 moles of ammonia, and they're saying at equilibrium, 0.4 moles of nitrogen were formed. Calculate the Kc. So step 1, write the balanced equation. So I wrote the balanced equation. Step 2, draw a beautiful ice table and fill in the missing blank spaces. So I drew my ice table, which you can notice right here, and I filled in the missing blank spaces, and I've shown you how to fill it. After that, and your ice is ready, ask yourself, am I potting the rice or coating the ice? If you're coating it, get the concentration. If you're potting it, get the partial pressures. So for this case, they wanted Kc, so meaning members, they wanted us to coat our ice. So we coated it by getting the concentration, which is simply moles divided by volume. Okay. After doing that, we went to the question and saw that they wanted the Kc. So if you want the Kc, to answer that, step 1 is to write the formula, which is this one. Step 3, substitute into the formula, which you see I've done here. And you notice the brackets I'm using when I'm substituting. The brackets I'm using here are not the same as the ones here. These ones here that you see, the square brackets, these ones that look like this. Those square brackets in chemistry, they represent concentration. So we don't just use them anyhow. Whenever you use them, you must be referring to concentration. And then these normal brackets that you see here are the normal mathematics brackets. So the moment I finish writing the expression, I drop the square brackets and bring back my normal brackets. Finally, I simplify. Like I said earlier, if you are good at mathematics, you don't need to do this step. You can just do this and give us the final answer. But my recommendation is you do it such that your work flows and you're enjoying. You sit in an exam and you are doing things step by step, and you're also enjoying whatever you're doing. And then finally, you have the value. I'm not calling this the answer. I'm calling it the value. Why am I calling it the value? Remember, it is not the answer. The answer has the value plus the units. Always know that A is V plus U. So the answer is the value plus its correct unit. That must be there. So we have our value here. We also have our correct unit. Those are the parts of my answer. So that is case 1 to case 3. Now, case 4 is a percentage thing, and it may require me to explain things in some good detail like I've done today. Today, I came to eliminate some errors and to wrap up whatever we have seen so far in a better and more organized fashion. Now, not to confuse, for this lesson, I'll close it from there and leave some numbers which you can look at to solve numbers for case 1, for case 2, for case 3. So the very first number I'm going to leave is this one, which says, I'll leave like 3 numbers, 1 for case 1, 1 for case 2, and 1 for case 3, and we shall call it a lesson for today. So the very first one says, number 1, a 2.0 decimeter cubed vessel contains 0.80 moles. Okay, let's make it a 4 decimeter tube instead of 2. A 4 decimeter tube vessel contains 0.80 moles of sulfur dioxide, 0.50 moles of oxygen, and 1.6 moles of sulfur trioxide. Calculate the case C. So this is a number in the one I did as case 2, I guess. Case 1, where you only have, okay, case 2, where you only have the moles at equilibrium. Okay, number 2, when you have initial moles and the moles that reacted, probably. Let's see case 2. Oh, what's wrong with my writer? Just a minute. Okay, so case 2 says, which would be in my number 2. Okay, let me set it this way. Initially, okay. Let's still use sulfur trioxide and sulfur dioxide. A 3 decimeter tubed vessel, a 3.0 decimeter tubed vessel, a 3.0 decimeter tubed vessel, initially contains 2.40 moles of sulfur dioxide and 1.5 moles of oxygen. At equilibrium, at equilibrium, 1.2 moles of sulfur dioxide remains. Calculate the case C. Okay. And then finally, this one says, a closed vessel initially contains 2.5 moles of phosphorus pentachloride. At equilibrium, 0.75 moles had dissociated. Then calculate the case C. Okay. So you should remember that you should always write a balanced equation first. So if the moment you fail the equation, then things are made wrong. So the very first thing that should work out is the equation. I want to close this lesson from here. Thank you so much for attending. Till we meet again, I'll pass it back to Miss Anita to take it up from there.
Thank you so much, Teacher Solomon, for endeavoring to deliver your knowledge. to our learners. Thank you for always showing up and showing out. This and all the other live classes are recorded and are uploaded on the Magezi Harvest platform that you can access via harvest.magezi.space.